Okay. All right, cubic functions. A cubic function, that's not really a surprise, is it? A cubic function is a polynomial function of degree 3. This is the form. A, B, C, and D are real numbers, and A does not equal 0. The parent function is simply y equals x to the third. All right, turn the page. We have turning points. All right, so we don't actually have a piece of rope, but we have a nice picture of a piece of rope on the next page. All right, take a piece of rope laid on the table so you can see that happening there. And it says put 2 turning points on it. Remember that the turning points would be the local maximum and the local minimum. Okay, right there, local max and local min. So that it looks like photo A. One of the turning points is known as the local maximum. It's not the absolute maximum because the graph goes to infinity. And one is called the local minimum. It's not the absolute minimum because the graph goes to negative infinity. And so this is the most common shape of a cubic function. However, it says first, between those two, this is called the point of inflection. So that goes here, point of inflection. And the point of inflection is all of those circles. Do you see how there are things circled on each graph? The circles are indicating the point of inflection. So the point of inflection is the place where the graph changes concavity. It's very easy to see it when you have this shape right here, because you can see that this is opening down, that's concave down, and this is opening up, this is concave up. As you stretch, so see, think of this as a piece of rope, and as you stretch it, it's harder to locate that point of inflection in between, but you can slightly see that concavity, concave down, and then concave up. So what does it say after that? For each example, the graph changes from concave down to concave up at the circled point. That's your point of inflection. All cubic functions undergo a single change in concavity, and this change occurs at the cubic's point of inflection. Cubic graphs have 180-degree point symmetry about the point of inflection, which means that if I were to reflect this piece horizontally and then vertically, it would be this piece right here. So this is its symmetry. Remember that for the vertex, we had that formula for the x-coordinate of the vertex, which was negative b over 2a. For the cubic function, the point of inflection can be found at x equals negative b over 3a. So now it says, now imagine the ends of the rope are pulled, and at some point in the pulling, it will become something like that in photo B. The turning points have merged to form a single point known as a horizontal point of inflection. Because the line almost goes, or the curve almost goes horizontal there. Or alternatively, it can be called a stationary point of inflection. Then if you continue pulling the ends of the string, you're going to get something like photo C. If it was an actual rope, you could make a straight line out of it, but a cubic function will never have a straight line. It will always have that curve, that concavity. It just will be so slight that it might be hard to see. All right, when you're ready, turn the page. I see a few people writing, but when you're ready, turn the page and look at the forms of a cubic function. You'll notice that they look similar to the forms of the quadratic function. The quadratic function had 2 factors. How many factors does the cubic have? You can have 3 factors unless the second part is not factorable. So let's look at that. Forms of a cubic function. So here's your general form. Here's your translated form. Here's the factored form when there's 3 factors and an a value in front. And then this is, if this one does not factor, then your factored form would have 1 linear factor and then 1 quadratic factor. The translations are going to work the transformations are going to work just like the ones in the quadratic function. The a value in front of it can tell you if it's dilated in which way. So if a is greater than 0, the graph is increasing if it's positive. And if a is less than 0, the graph is decreasing. H is going to translate you horizontally, k vertically, and there'll be a point of inflection at HK if it's written in the translated form, if it's written in that form. All right, so take a moment to process all of that and consider this part right here. See what you can do on your own first, looking at these and comparing them up here. 1/2 here, right? It's increasing because 1/2 is greater than 0. Is it more or less steep than the parent function? What is that 1/2 going to do? Is it going to stretch it more steep or is it going to compress it less steep? It's going to compress it less steep, right? So because 1/2 is less than 1, so it's going to be less steep. All right, and then to find the coordinates of that point of inflection, that's when we need to multiply the whole thing out. So I'm going to write it out. Not really a whole lot of workspace here, unfortunately. Okay, I'm going to use a space over here. So I have 1/2 x squared. Okay, you're going to get a minus 3x and a minus 3x. You can put those together to make minus 6x, just to save space and not have to write that line out. So minus 3x and minus 3x makes minus 6x, and then negative 3 and negative 3 gives you 9. And then you can multiply. Some people distribute from the trinomial to the binomial. I personally like to go from the binomial to the trinomial. Just pick a starting one and distribute to the other one. So I'm going to distribute from the binomial to the trinomial. So this times this times this times this. Does not matter if you want to go the other direction. And then I actually like to line these up. So negative 3 times x squared, I'm going to line it up here. Negative 3 times negative 6x, positive 18x, and negative 3 times 9. And then finally I have to distribute that 1/2. I think I can do it over here. So 1/2 x cubed minus 9/2 x squared plus 27/2 x minus 27/2. And now we can use the formula. Negative b over 3a, and that's going to be 9/2 over 3/2. Emily Bro. Hi. Okay. Sure. Thank you. I'll send her. Bye. Hey Claire, it's Mr. Tubbins for you. He just said to go for your meeting. All right, so I get 3. So that's the x coordinate, and then how do I find the y coordinate? Substitute it in, right? Yeah, so substitute that back in here. You could just put that in your calculator and then use the table if you don't feel like doing all that multiplying, okay? So I'm going to do that. You guys can do that as well. I think I need to move it though. So 1/2 x to the 3rd minus 9/2 x squared plus 27/2 x minus 27/2. And then I can look at the table. And it looks like it's 3, 0. So 3, 0 is your point of inflection. All right, so to plot the graph, some important things that we want are we want to graph x-intercepts and y-intercepts. And so we only have one x-intercept, and where will it be? Use your factors, guys. If you set your factors equal to 0, you get your x-intercepts, which are what? They're all at 3. So that would be like right here. My y-intercept is going to be at negative 13/2, which is way off my graph, so I can't graph that one. So I just need to graph a few more points. So I'm going to graph points that are around my point of inflection. So since this one is at 3, you're going to graph points below it and above it. So 1, 2, 3, 4, 5 should work. And luckily, we have this in our table here. So we should be able to grab the values from there. So negative 4, negative 0.5, 0, 0.5, and 4. And then we're going to graph those. Sorry, you couldn't see any of that because it was behind the calculator. All right, so when you finish that one, I want you to turn the page and try 2 and 3. All right, to find the x-intercepts, you make the y 0, and if I make the y 0, the zero product property says one of these factors has to equal 0. So you can write x plus 4 equals 0, x plus 2 equals 0, and x minus 1 equals 0, and you can solve them. You could have used the table to find the same numbers. All right, so if it said just to find the x-intercepts, I would have had to write those as points, but it just says find the x values of the x-intercepts, so I'm okay to leave it like that. I'm going to mark them negative 4, negative 2, and positive 1. Now to find the y value of the x-intercept, you have to make the x's 0. So you could multiply the whole thing out, but it might be easier to just do it this way. Okay, So 4 times 2 is 6, times negative 1 is negative 6, and then there's a negative in front, so I just get 6. All right, and so now that we have those points, that's actually enough to sketch in the general shape. It's not exactly that shape, but it's close to that shape, and that's good enough for a sketch. You could graph it in your calculator just to make sure that you're generally in the right place. All right, so Ryan found my mistake here. 4 times 2 is 8. Nobody else is going to tell me? You're just going to keep that little secret for me? All right, so it should go all the way up to 8. Hello. The volume of a sphere has the formula V equals 4/3 pi r cubed. The graph relating r and v is shown here. Fill in the table of values for the equation, writing your answers. It says correct to 2 decimal places, but we're actually going to leave them in terms of pi. So in terms of pi. The problem with in terms of pi is it's hard to graph in terms of pi, but we're not asked to graph because we're given a graph, so we can do this. All right, so if I put in 1 cubed is 1. So it's just going to be 4/3 pi. If I put in 2 cubed is 8, and then 8 times 4 is 32, so we should get 32 over 3 pi. Okay, then we're getting to the point where you might want the calculator. You're going to do 4 cubed. Oops, I'm not in there. Second, quit. So 4 cubed. And then we have to multiply that times 4/3. And then you can go math fraction. Notice I didn't put the pi in there because we're going to just leave the pi in our answer. So we get 256 over 3 pi. All right, if you haven't yet, answer 5. Why does it say 5 and 7? That's weird. All right, but let's do 5 and 7. Just pay attention that that's 5 and 7. Oh, we did. Good point. All right, I'm going to try to catch up to you. So what I'm going to do is I'm going to do second enter to get back to the last thing I typed and just change my 4 to a 5. So I'm getting 500 thirds. Did you guys get 500 thirds? Okay. Pi. And then 7. So I'll do the same thing. Second enter brings me back to the last thing I typed. And then change the 5 to a 7. (1,372 thirds) pi. All right, so a sphere has a radius measuring 4.5 meters. Its volume falls within which of the following intervals? So 4.5, I guess we can just put that number 4.5 in there, right? And see which one it's going to be. So I'm going to do 4.5 to the third times 4/3. And then do math fraction. Okay, so I get 243 over 2 pi. So 243 over 2, actually, I think I want that not as a fraction. All right, I get 121.5 pi. Can you guys see which interval that's in? This one, right? Yeah. All right, it says to use the graph to find the radius of the sphere, but I don't find the graph to be that helpful. Well, maybe it is. let's look at it together and see if I can see it better on my screen. It says 288 pi. Oh, there it is. Okay, it's not that bad, is it? This is it right here, right? Can you guys confirm I'm looking at the right thing? Because my sight is terrible. That says 288 pi? Okay. So if we go over, then we should be able to see that the radius is how much? 6. Good. That's good? Okay. One more problem, guys. This one is a little bit tricky, so we are going to spend some time with the setup on it. May I turn it? Okay. A box without a cover is to be constructed from rectangular cardboard measuring 6 centimeters by 10 centimeters by cutting out 4 square corners of length x centimeters. Let V represent the volume of the box. So here's what they're doing. They're taking a rectangle and they're cutting these corners out, square corners like this. Okay? And then they'll fold the box up on these lines here so that it looks like a box. Okay? So they cut out the corners and they fold it up and it should make a box. And it says that the square corners have length x. So this would be x and this would be x here. So the squares have x on each side. They're squares, so it makes sense that they match. Okay, it says the rectangular cardboard measures 6 centimeters by 10 centimeters. So this whole thing is 6, the shorter side. And then the longer side is 10. I don't really have a good spot for that, but let's do it anyway. Okay, so this whole side is 6 and this whole side is 10. So we need to express the volume of the box in terms of x. So remember that the side of the box is not going to be 10 because we cut these out. The side of the box is going to be this here. So if I have to express this side in terms of x, it wouldn't just be 10. It would be 10 minus what? It's a good question, guys. Would it be 10 minus x squared or 10 minus 2x if we're just talking about the length? Yeah, so 2x for the length. X squared, I think, will come up when we find the volume. Or maybe x cubed when we find the volume, right? Okay, so this side here is going to be 10 minus 2x. And that means that this side here would be 6 minus what? 6 minus 2x. Good. All right, so I know the length and the width of the box. What's going to be the height of the box once I fold those up? What do you guys think? Sophia suggests x. When I fold those up, will the height of the box be x? I think you were right the first time. When I fold this up, this here is going to become the height of the box, right? And that's a length of x. So it's going to be x for the height times 10 minus 2x for the width times 6 minus 2x for the length, and that would be your volume. You have to multiply all those out. And it says to write it in factored form. Why is that not a good factored form yet? No, look at your factors. Your factors actually need to be factored more. What can I factor out of my factors? A 2. You see how I can factor a 2 out of this one and out of this one? Okay. So if I take 2 out of this one, and I take 2 out of this one as well, I'm taking 2 out twice. I took 2 out of the first factor and the second factor, so it has to go back in there twice. 2 times 2 gives me 4, and then the x, and then 5 minus x, and 3 minus x, and that's your factored form. All right, I want you to take a moment to think about what range of values of x the volume function will be defined for. Okay, because remember, none of the sides can be 0 and none of the sides can be negative. So look at the numbers and see what numbers we can use for x, and then we're going to plot a graph of the volume function. Sorry, between 0 and 3. So we're going to plot this volume function, but we only really need to plot points from 0 to 3. So we could substitute numbers in, or we can put this in the calculator and get a table. And I'm thinking we want to maybe do that second thing. So let's graph this and then look at the table so we can plot our function. Y equals, you guys should be doing the same right now. And I'm going to do second table, and then
if it's like 6, for example, we multiply the negatives together and it would be positive.
That's a good point.
It should be like negative times 4x.
Mm-hmm.
And it, so like 6, 4.
But the side would be negative. That's the problem. Right, so if we made it, that would mean that side was -6, but it would make a positive volume. I agree on that. All right, so even though we're not including 0 and 3, those are endpoints, so I'm going to include them in my table of values. So 0, 1, 2, and 3, I'm going to put in there. Okay. So here, I'm going to use an empty dot to indicate not including that point, and then the same thing at 3. An empty dot not including that point. And then I have 132. And then I have 224. Okay. And remember that this is going to end up being a somewhat smooth curve. So trying to figure out how that's going to look. I think it's going to go up past this point so that it looks somewhat smooth, like that. And it looks like a parabola, but the reason it looks like a parabola is because we don't have the whole graph on here. We only have the part that makes sense. So the real graph would probably go like that. Continue on and make the shape of the cubic. Determine the volume of a box that has a height equivalent to the shorter dimension of the base. The base is the 6 minus 2x, right? And we want that to equal the height, which was x. And so we're just going to solve that. And what unit are we using? Looks like centimeters, is that right? So that would be 2 centimeters for x. And so then when we substitute 2 back in for the volume, we would do volume equals 4 times 2 times 5 minus 2 times 3 minus 2.